I'm going to show how the residence time distribution, which we could determine from a tracer experiment that's described in other screencasts. So combining a residence time distribution with the assumption that we have segregated flow in the reactor, we can use that to calculate conversion for a non-ideal reactor. Whether that's going to be an accurate determination of the real conversion of the reactor depends on how good an approximation segregated flow is. So an important thing to keep in mind when we're talking about modeling reactor with residence time distribution is that the residence time distribution does not give us information on mixing, meaning exchange of matter between different fluid elements. And so we can make an approximation of complete mixing, or we can make an approximation of segregated flow, and they're going to give us the extremes of what the actual conversion is going to be. And the mixing can be quite important in determining, for example, in polymerization reactors, the molecular weight distribution. And for polymerization reactors where we have high viscosities, mixing indeed can be quite important. We have a number of reaction steps taking place. The equation we'd use if we know the residence time distribution and we want to calculate the concentration leaving the reactor. So I'll put a bar to indicate this is the average. So this is the exit concentration from the reactor. That's an average. And what we're going to do is integrate over all the different times in the residence time distribution. And so what we will assume is we have essentially a number of batch reactors, and the residence time distribution will determine how long they stay in the reactor and how many of them there are. So we're going to calculate as a function of time the concentration, and this is for a batch reactor. So we're assuming if we had a batch reactor, how does concentration depend on time? And then we're going to use the residence time distribution, which we obtained from a tracer measurement. And essentially we're adding up all those from 0 to long enough time to account for all of the reactions. So we're envisioning that a large number of batch reactors are moving through the reactor independent of each other, and how much time they spend in the reactor we get from the residence time distribution. So this E of t, the residence time distribution, in words, it's a fraction, and it's the fraction of the packets, large number of molecules but small packets that don't mix with each other, spend a time between t, so the t that we're using integration in a given time, t, and t plus dt. That's what this fraction is. If we had first order reaction, then the residence time distribution is sufficient to give us the exit conversion. But if we have another order reaction, less than first, greater than first, it's not sufficient. So what we're going to do to demonstrate this is take an ideal CSTR. Ideal CSTR, we could use our normal way of calculating, just a mole balance, assume complete mixing, and so all reaction is at that concentration, a final concentration, and we're going to compare that to an ideal CSTR where we have segregated flow. And here are the parameters we're going to use. And so if we are looking at the complete mixing case, steady state, it's the molar flow rate into the reactor minus the molar flow rate out, rate of reaction times the volume, where this is the volumetric flow rate, the concentration in, the volumetric flow rate, the final concentration leaving the reactor, and then second order reaction minus K, A is our reactant, concentration of A squared times volume, and important to keep in mind this concentration is the same as this concentration. We're assuming well mixed. So we can substitute the numbers into this and calculate the conversion. So I've shown substitution of the numbers with the units, reducing to this quadratic equation. The solution for the quadratic equation is given here, and then the conversion is the inlet concentration, outlet concentration over the inlet concentration. Since it's liquid phase, we can use concentrations, and the conversion 0.79. So this is for complete mixing, which is what we're assuming when we use the CSTR and assume everything mixes so it's at that final concentration. Now let's contrast that to where we're going to assume segregated flow. So I've just copied the equation down again for segregated flow. Second order reaction, if we solve the mass balance, and that's certainly done in other screencasts, the equation relates the concentration, it's a function of time, to the rate constant, initial concentration. Ideal CSTR, the residence time distribution, which is also derived in other screencasts, is given here, where tau is the volume of the reactor divided by the volumetric flow rate. So in this case, 150 liters over 100 liters per hour. So tau 1.5 hours, the base time, in this case residence time in the reactor. So we can substitute the numbers into this equation, the integral. So I've substituted in the numbers without the units just so this won't look too confusing, but you should certainly double check the units are correct. And then if I do this integration numerically, I end up with a concentration of 0.68 moles per liter to two significant figures, and then I can calculate conversion in the same way. And so when I do the calculation of conversion, I get 86% conversion compared to 79%. So the conversion for segregated flow is greater than for complete mixing. And so the important point here is that there's a difference in conversion for an ideal CSTR depending on whether we assume complete mixing or we assume segregated flow. So the residence time distribution is not sufficient for us to determine what the conversion is going to be in the reactor. We need some information about mixing. So I've added at the end here the Mathematica commands for those who be interested. How I got to numerical values, certainly could have used the quadratic equation, but it's certainly very easy, particularly when we have more complicated equations, to use the find root command, where basically I've written down the equation here, and then I indicate the variable I'm solving for, CA, and indicate my guess, my starting value or approximation to the solution. And then over here I've written the integral, which is a little more difficult to do analytically, very easy to do numerically. We're integrating from 0 to infinity, so in Mathematica I integrated from 0 to 10 and then 0 to 100, got the same answer. And so it's just an integral command in Mathematica, and it very directly outputs the solution.